So here we go on Lesson B of Unit 1B, motion on a ramp and relative motion. In this lesson we're going to examine the problem of motion on a ramp or incline. There's three reasons we're going to look at this. We're going to look at it's good practice at using vectors. It's a simple problem that we can find an exact solution to. And it seems kind of abstract, but it has real and important applications. So we're going to begin with looking at a constant velocity example to give us some practice with the vectors and components before moving into the general case of accelerated motion on a ramp. So here what we have is a car that drives up a steep 10-degree slope at a constant speed of 15 meters per second. After 10 seconds, we're going to figure out how much height it's gained. So what we're looking at here is we want to pay attention to the y component of this object's velocity, this car's velocity. So we're saying, okay, this car is basically driven at a constant velocity straight up by looking at the y velocity. So we know that its initial velocity is, its total velocity is 15 meters per second up this ramp. The ramp is a 10-degree angle, and what we're looking for is the height that it's gained. How high up the ramp is it? In order to solve this, we're going to want to know the y component of the velocity. So Vy equals v sine theta, and then we substitute in our values. And we end up with a y component of velocity of 2.6 meters per second. So we're saying as though we're looking at this as though the car has driven straight up at a constant 2.6 meters per second, and so we can use our constant velocity equation to figure out then the height that it's gone. So we plug in that 2.6 there for the v. We're finding y 10 seconds. Y is 26 meters. Okay, so it's gone 26 meters, an elevation of 26 meters. So now we want to look at accelerated motion on a ramp. Okay, so when an object such as this ball rolls down a ramp, I mean clearly its acceleration points down that ramp, right? So it's going to start up here, it's going to gain speed as it rolls down the ramp. It's going to be going faster there. It's accelerating down the ramp. But let's look at a condition where the object, say, is rolling up the ramp. If we were to do, say if we take this and we said we were going to roll the ball up the ramp this direction from the bottom to the top, and we wanted to draw a motion diagram of that motion would look like this. The ball is rolling up the ramp. It has a higher rate of velocity at the bottom of the ramp, and it slows to a stop at the top of the ramp and then turns around and comes back. So this is just the up the ramp part of the motion. And if we did the motion diagram for it, we know that the acceleration will always point toward the longer velocity arrows. So our acceleration points down the ramp. The point here is that for an object that's moving freely on a frictionless ramp, its acceleration is always going to point down the ramp. Okay? How can we figure out, though, the magnitude, the size of that acceleration? So let's imagine we've got a box, and it's sitting on a flat surface like this. Its acceleration here is obviously 0 meters per second squared. Now if we take its surface and we put it perfectly vertical, we've got that box on there, we release it. What's its acceleration going to be? Well, its acceleration will be 9.8 meters per second squared down. Okay? So when the surface is perfectly horizontal, 0 acceleration, and when it's perfectly vertical, we have a 9.8 meters per second squared acceleration. So that tells us that the acceleration of an object moving freely on a ramp has got to be somewhere between 0 and 9.8 meters per second squared. In order to find out the size of that acceleration, we can draw a vector diagram of that acceleration. Here we have here's our object on the ramp. It's sliding freely down that ramp, and we're assuming that this is a frictionless ramp. Okay. Free fall acceleration would point straight down. So if we split the free fall acceleration into its components, we'd have a y component here that would be perpendicular to the surface of the ramp, and we'd have an x component here pointing down the ramp. Well, it's this x component of the acceleration, of the free fall acceleration, that supplies the object with its acceleration down the ramp. So that's the component of the free fall acceleration that accelerates down that incline. Now let's take a minute and look at this angle here. The angle of the ramp, when we're told that the ramp has a certain angle, that angle is always measured from the end of the ramp right here. So if we were to do an analysis of, say we were to draw a triangle here of this ramp, okay, and we were to move that triangle and place it right here, what we're going to find is that this angle and this angle are the same. These are similar triangles, okay? So when we look at this vector diagram then of this free fall acceleration, the angle created by the components of that acceleration are the same angle as the ramp. So what we can do, if we want to find AX, then we notice that AX is opposite that angle. Therefore, AX is A sine theta. Okay. Now, when we know that A is free fall acceleration, we can replace that with a G, and we get a general expression for acceleration down a ramp of A is equal to G sine theta. Now this plus minus on here, this indicates that sometimes our G will be positive and sometimes our G will be negative. So let's look at some examples of each of those conditions. So the Willamette Pass ski area in Oregon was the site of the 1993 U.S. National Speed Skiing Competition. Each competitor's speed was measured at the end of the acceleration portion of the track, which has a reasonably constant slope. During that acceleration phase, the skiers traveled 360 meters while dropping a vertical distance of 170 meters. We want to find the fastest speed a skier could achieve at the end of the run and how much time that would take. Okay, so to begin this, right, we know that we start with zero initial velocity. We want to find out how fast they're going at the bottom of the ramp and how much time that it takes. To start with this, we know that the ramp is 170 meters tall and 360 meters long. So these are the dimensions of our ramp. We can find the angle of our ramp from that, just like this here. Okay, so our angle is a 28-degree ramp. So in this situation, right, we're starting at zero velocity here. We're speeding up as we go down, so our acceleration points down the ramp, and our velocity points down the ramp. So velocity and acceleration are in the same direction here. Therefore, we're going to have a positive acceleration. So because this object is moving freely down the ramp, we can use G sine theta to get us that acceleration. So we just plug in 9.8 sine 28. Our acceleration down the ramp is 4.6 meters per second squared. And then all we have to do is now apply kinematics equations to figure out our speed at the bottom of the ramp and our time. So our speed at the bottom of the ramp ends up being this 58 meters per second using our third kinematics equation, and our time at the bottom of the ramp ends up at 12 seconds right there. So this 58 meters per second is about 130 miles per hour. So that's going pretty fast. All right, so let's look then at a condition where our expression for acceleration down a ramp, acceleration on a ramp, would be a negative. So here we've got a classic wooden roller coaster. Has cars that go first down a big hill and then up this hill. Okay, so our cars come down this way and then up here. Okay, the cars are going 25 meters per second at the bottom of the ramp. So our initial velocity is 25 meters per second at the bottom of the ramp. And it takes them 2 seconds to climb that hill. Okay, how fast are they going at the top? Now, anybody that's been on a roller coaster knows that when you start at the bottom of a hill, you're going faster than you're going at the top of the hill, right? So our velocity at the top of the hill, which is what we're looking for, must go down, okay? So our acceleration in this case obviously has got to point down the ramp, because if we were to do a motion diagram of this, our longer velocity arrows are down toward the bottom of the ramp. So our acceleration points down the ramp, our velocity points up the ramp, which is going to mean that we're going to have a negative acceleration. So our acceleration in this case will be a negative 4.9 meters per second squared. And once we figure that out, then we can apply kinematics equation to find out the speed at the top of the ramp. So we'd apply the first equation, we end up with 15.2 meters per second. So now let's talk about relative motion then. When we first talk about relative motion, one way to look at that is this, ask yourself, you're sitting in a room right now, are you moving, right? If you look from the perspective of the room, no, you're not moving, right? But if you were to take yourself outside of Earth and you look at yourself from there, Earth is moving, therefore you're moving, right? So that's kind of what we mean by relative motion, is that velocity measurements are going to be different in different frames of reference, okay? Another way to look at it is if you're on an airplane and you walk at, say the airplane's moving at 500 miles an hour, and you walk from the back of the airplane to the front of the airplane at 2 miles an hour. So how fast are you going? Well, to the occupants of the airplane, you're going 2 miles an hour, right? If there is an observer outside that airplane stationary on the ground sees you, you'd be walking at 502 miles per hour. It's all based on the frame of reference. Another example would be, say you're in this airplane here, and you drop, here's a stunt dummy being dropped from this airplane. That's what the dot is. So from the reference of the airplane continues on with that as it falls, and to the airplane, it seems as though it drops straight down, right? An observer on the side, the stunt dummy follows this parabolic path instead, because it follows along with the airplane and falls at the same time, falls down at the same time. So let's take a look at this example. We have a boat that's heading north, crossing a wide river with a velocity of 10 kilometers an hour relative to the water. The river has a constant velocity, a uniform velocity of 5 kilometers an hour due east. So we want to determine the boat's velocity with respect to an observer on the shore, and then we'll find out if the river is 1 kilometer wide, how long it's going to take to cross the boat, for the boat to cross, and how far downstream will the boat be. Okay, so let's analyze this a little bit, right? So if you're on this boat, first, you're moving, you've got a velocity this direction. As far as you're concerned, you're going straight across the river. The river is also flowing under you at 5 kilometers an hour. So you're going at 10 kilometers an hour, and the river is flowing at 3 kilometers an hour. Okay, this is going to give us a resultant velocity. So if you're on the shore watching this, you're watching this boat not travel straight across the river. You're actually kind of moving off to the side, right? So you're going to end up, so if, on the other side, if you started at this point, you're going to be drifting down here at some point, okay? So what we want to find when it talks about finding the velocity with respect to an observer, we're looking for then this resultant velocity. So to find that, we'll just apply the Pythagorean theorem like we learned with our lesson on vectors, and we get VR squared equals 10 squared plus 5 squared giving us a resultant velocity then of 11.2 meters per second. So here is our resultant velocity of the boat across the river. That's how fast it would seem to an observer on the shore that the boat is going. Part B tells us if the river is 1 kilometer wide, how long is it going to take for the boat to cross? Well, when we look at this, right, to cross the river, the only component of our resultant velocity that is getting us across the river is the boat's velocity of 10 kilometers an hour. Okay? So the only component of the resultant velocity that is getting us across the river is the 10 kilometers an hour, the boat's velocity. So because this is a constant velocity for the boat, we can apply the constant velocity equation, and we end up with 0.1 hours, which 6 minutes. Okay. Now we want to find how far downstream the boat will be. Well, the only component of this resultant velocity that is pushing us downstream is the river's 5 kilometers due east. So again, we can just apply the constant velocity equation to find that will be half a kilometer downstream. Now, one thing to point out and just be aware of with this problem, right? We're used to working in meters per second and that sort of thing. In this problem, everything's in kilometers per hour, so I've reported my answer as 0.1 hours and half a kilometer. Okay, so that ends lesson B of Unit 1B, and we'll see you in class.